Hey guys, Buildzoid here, and today I'm gonna go over the e-power plan for the HD7970 DirectCU2 that was sent in by Rave. So originally I was thinking of actually tacking on a PCB breakdown as well, but that wasn't really working out because the video was ending up really long, and also because I just kept thinking of things to talk about. So let's see if I can do it properly this time. So I want to make an e-power out of this card. Why? Because the core is dying. The card will basically fail, it'll fail to run if you try to, it'll crash if you install drivers, which basically means the moment the card hits 3D clocks, it's so unstable it dies. Because what happens after you install the drivers is the first thing that, basically, once you have the drivers installed during Windows 7 startup, the card will actually go to full speed. On Windows 10, when the driver initializes, the card will go to full speed. When that happens, card crashes, you get a black screen, you have to shut down the system because the card is hanging at that point. In theory, you could probably try bake the card back to life. But instead of having an unreliable HD7970, I'd much rather have its reliable VRM. So the plan is to cut the VRM off of this card, because I have another 7970 that's better, and quite frankly, ultimately I'm probably going to be I'm interested in picking up more 7970s over time anyway. So it's just like this isn't a huge loss because it doesn't bloody work, and at least I can have a decent VRM. This is not an incredible VRM. The vCore VRM is this block right here, which is an 8-phase controlled by this chip right here. And these chips right here, those are IR3598s. Those are dual drivers. That is an ASP 1211, so you're kind of getting a PCB breakdown. I'm not going into the details though, but that's an ASP 1211. That's an 8-phase controller. And IR3598s, if you want to know what they are, you should go watch some other videos. I cover these chips quite a few times at this point. The VRM phases themselves are made up of a high side MOSFET and two low sides. The high side FET is an on-semiconductor 4955N. This is a kind of slow MOSFET for being a high side, rather high capacitance as well. But it'll do just fine. And the 49, then the next the low side MOSFETs are 4937Ns from, again, on-semiconductor. These are 4 milliohm RDS on low side MOSFET. So that's actually kind of high, but there's two of them in parallel, so it works out to be pretty decent. And this VRM is definitely an upgrade over what you would find on like a reference HD7970, though that's not much of an achievement. Because honestly, the reference one is like a 5-phase or a 6-phase, depending on what the manufacturer decides to configure it for. Either way, we get basically this is kind of bog standard ASUS VRM. In terms of actual thermal performance, it should be very similar to the 780 Ti I did recently. So if you just want to get some rough current figures, it's not going to be dead on. These are different MOSFETs from that card, but they're similar spec-wise. Like, they're not that far off in terms of specs. So the thermal performance should be, the heat output should be similar. Thermal performance obviously depends on what kind of cooling you throw at it. But yeah. So that's the 8-phase vCore VRM here. Above that, there's the memory VRM controlled by this chip. MOSFETs are the same thing. One high side, two low sides, 2-phase. This chip, I have no idea what it is, but it is a 2-phase. And speaking of chips that I don't know things about, the ASP1211 does not have a public datasheet, which is not going to stop me. I am way too damn good at this. No, I'm just overly confident. And probably I'll still succeed because there's not that many ways to wire up a voltage controller. At least not many ways that make sense. I mean, if you wanted to make it convoluted and complicated, you could, but why would you do that, right? Like, you'd make a pretty terrible product if it was intentionally hard to use. So, anyway, so that's your memory up there. And, yeah. I do want the memory VRM actually working, and I do actually want to get memory VRM control. Now, this one is actually a problem, unlike the ASP1211 down here, because, so this being an ASP1211 is a international rectifier part, just rebranded for ASUS to be the Digi Plus thing, but it's an IR, international rectifier chip. And that means it's going to have a feedback circuit that basically looks something like this. Just draw the chip out right here, right? So 12, 11, and then we have 2 pins, and one of them is going to be VS plus, and one of them is going to be VS minus. So basically, this goes to ground behind the GPU core, and this goes to a capacitor behind the GPU core, positive side of it. Now, well, this goes to the V-core power plane behind the GPU core. Now, the way this is wired, which makes it so easy to find, is that it basically looks like this. No, oops, not a resistor. You get a capacitor, and then this goes basically straight to ground, and this goes straight to V-core. So the reason why it's so easy to find is that basically you just need to go around the chip and find a capacitor that registers a very, very low resistance across it. And that'll basically tell you found what you're looking for, because that's the one that's wired ground and V-core. Because the thing is, since basically the only thing between the, in parallel with this is the core, the core of a GPU is very low resistance. On a 7970, I think it's around 3 ohms when it's turned off. So basically, you find a capacitor that reads about 3 ohms, or actually, it should be higher, because the one thing I did leave out there is generally some resistors on coming after, after the capacitor, there's generally some resistors on the lines. They're not literally straight to V-core and ground, but those resistors are generally around 1 ohm or 2 ohms, so more or less straight to ground. They're very low resistance. Though on some cards, especially power boards, those resistors are actually 100 ohms, which I think is to make the hot wire functionality, like the forward voltage sense functionality on those cards work. But on this thing, they'll be very low resistance, so it'll just be a matter of finding the capacitor like that. And on the off chance that I don't want to do it this way, and I want to, do it some other way, this card is, it's not a matrix card, but it does still support some level of extreme overclocking, because it has these points right here. We look at the back of the board, you have, this is a read point, that's a control point. That is a read point, that is a control point. These two are for V-core, and these two are for MEM. And these are for, as the label says, VDDCI. And this one's the control, and this one's the measure. Now, I don't actually care about these because, I'm cutting the card right here, right? I'm not, so this is going to be part of the card that I'm going to scrap. And that's all going. This is the part I care about. But these voltage read points and control points basically allow me, in theory, to basically figure out how these are wired up. Because as far as these are, Asus doesn't put these on. Actually, they do still put these on cards. These are basically the GPU hot wire, connection points. And the way these generally work is they literally just allow you to skew the feedback circuit through a potentiometer, or you can get a, I think, I forget the name of the part right now. Oh, well, it doesn't really matter, but you can, there's basically, by just changing the voltage, the resistance to ground from one of these, you can change the you can change the output voltage of the VRM. So the plan is that I'll figure out how these are wired up, and then basically trace them back to the relevant chips, especially this one. This one's a massive problem because I don't know who even makes this, so I have no idea how it's wired up. The nice thing about International Rectifier is that they use this circuit so much. I don't think I've seen an International Rectifier chip with anything other than this, now that I think about it. Then again, I've not seen an International Rectifier chip that was, intentionally super low cost, so that might be part of it. But either way, this, IR uses this on everything, and Asus uses IR a lot. So basically, if I see a Digi Plus ASP branded chip my first assumption is look for this. It's probably the right circuit. And this is how I, and also on the Vega 64, this method of looking for a capacitor with, a very low resistance to ground is how I actually found the feedback circuit on my Vega 64 and then my Vega 50, and my Frontier Edition, my 64, my 56. Well, after I found the Frontier Edition, all of those cards have the same freaking PCB, so I had to figure it out only once. But yeah, basically just find the right capacitor and then the resistors hooked up to it, and bam, you got your feedback circuit for any international rectifier chip. I did the same thing for the A88X-Pro motherboard from Asus, because that board has a BIOS that maxes out at 1.9 volts, and I was running 32 nanometer AMD CPUs on it with LN2, so I needed quite a bit more than 1.9 volts. I needed I wanted 2.1, and I actually got up to 2.1, though I really that volt mod was so dodgy. It was really, really bad. But it did work. The only issue was the way I did it was that the potentiometer would get seriously hot, because normally what I do is I actually tweak the circuit to have a higher resistance towards the actual, because normally the resistance here is nothing towards VCore and to ground. So when you want to skew it, you need to put a very low resistance resistor or set the potentiometer really, really low. When you do that, you have quite a lot of current going through the potentiometer, so it gets hot. So normally I intentionally bump up the resistance toward on the sense lines, so that when you try to skew them, you don't need to use as low a you don't need to push as much current through the potentiometer, because that makes it get hot, and that's not fun. So yeah, where was I? Right, so this one's really easy to wire up, but this one, no idea. So I want to just steal it off of the voltage read points, because the way the voltage control points here, because the way those work, seems to indicate that they're basically going to give me exactly the same functionality as with these. I just need to figure out how they're wired up. So that's the plan to get the memory VRM voltage control going. Now, obviously, when you cut a GPU right across here, you run into some issues. The main issue is that, well, you only have plus 12 volts right here, right? These are the only power connectors you'll be left with, so you have plus 12 volts. And this can have some potential issues. Now, this card doesn't look like it actually has any of the 12, there's plus 12 volts on this, and there's plus 3.3 volts. So those are the two voltages that I'm going to need to, that we have 12 volts over there. But this one is the problematic one. So that one I need to add to this area of the card. The way I plan to do that, measure the resistance from the 3.3 volts pins of the PCIe slot to random capacitors in this area until I find one that measures 0 ohms, because there's going to be, and it should be pretty close to this chip actually. If this ASP1211 runs off of 3.3 volts, which I suspect it does, then it'll have a power supply, it'll have a bypass capacitor for its power supply, and that capacitor is literally just going to go from 3.3 volts to ground. And the moment I find that, it's just going to measure, the 3.3 volt side of it is going to measure 0 ohms to the 3.3 volt pins here, which I think I'm actually pointing to the wrong pins. I think those are 12 volts and those are 3.3. I'd need to check the pin out. I don't remember right now. I'm actually pretty certain I got that wrong. This is the 12 volt. Yeah, that is the 12 volt side. Well, there's a bunch of other pins in between there, so, but yeah, I have these flipped around. The 3.3 volts is to the 3.3 volts is next to this, towards this gap, and 12 volts is on that, towards that side. Though it's not this pin right here. I know that much. Either way, you can measure the 3.3 volts and 12 volts from this connector, and 3.3 volts is the important one. Find that one for a capacitor here, then wire up that capacitor to 3.3 volts. From a SATA cable. SATA extension cables are my preferred way of getting 3.3 volts as well as 5 volts, because they're not, the other option is that you buy a dedicated little buck converter or a low dropout regulator or some kind of other regulator to convert 12 volts into 3.3 and 5 volts. And the thing about that is it's way bulkier than if you just, use a SATA power connector. The other cool thing about using the SATA power connector is that if you literally only supply 3.3 and 5 volts off of that SATA power connector, you can actually use your power board in a multi power supply setup, where basically what you can do is you can shove 12 volts down the 8 pins from the secondary PSU. So PSU 2, right? That one's going to be providing the 12 volts. And this power supply just sits turned on all the time. And this is fine, because as long as these MOSFETs don't try to turn on, the 12 volts is just going to sit here on the input side and just be harmless. It's not going anywhere, because these guys aren't turning on. Now, the 3.3 volts, which I don't know where we'll wire that off of, but let's just pretend like I have a connect... Whatever. Plus 3.3... and plus 5, and I know plus 5 is actually important. Now, some cards don't need a plus 5 volts, but this does. And the reason why this does is this LDO right here, but also because of these International Rectifier 3598s. These run off of 5 volts. If you don't give them 5 volts, they don't turn on. So that's why we have this LDO over here. That's a 5 volt LDO. Without that LDO, these no worky. And if these no worky, the VRM can't turn on because those are the bloody driver chips. So naturally, we need to supply 5 volts. So the 5 volts and the 3.3 volts, you would put that on PSU1. And what that basically does is PSU1 is the PSU that also powers things like your motherboard, right? So, which, let's just go MOBO. And the thing about PSU1 is basically until you press the power button, these voltages don't exist. So the voltage controller and the drivers can't turn on. So the 12 volts will just sit harmlessly on the input side of the VRM. And this is exactly the same way that a multi-power supply setup works when you have the GPU running off of its own PCIe slot. Because as long as the primary GPU that's, well, the PSU hooked into the motherboard isn't getting turned on, there's no 3.3 volts on the card. And as long as the card doesn't have any 3.3 volts, the voltage controllers can't turn on. So the moment 3.3 volts is supplied, the voltage controllers turn on, and bam, now the VRM turns on, and everything works. So that's the cool thing about using the SATA connector. If you use the bucket, like if you just put like some kind of voltage regulator to convert 12 volts off of these power connectors into the voltage you need for the chip here, the moment you turn on PSU2, it would also turn on the entire VRM, which if the PCIe interface isn't, active, like you would seriously screw up your power sequencing doing that. And I'm not entirely sure if your GPU would survive that. I have a sneaking suspicion it might not. And I'd rather not test that. So the better way to do things is obviously to have the 5 volts and 3.3 volts controlled by the PSU that also turns on the motherboard, because when the motherboard turns on, the GPU will actually turn on with it. Instead of, your GPU running without the motherboard. Like, that doesn't work. You can see how that doesn't work. So, yeah, you want this VRM to turn on at the same time as the motherboard does, not before it. So that's the other cool thing with the SATA connector. At least in theory, that should work. So that's why I use the SATA connector. I did point out the 5 volts LDO. What haven't I covered? I've covered the feedback situation, this situation. How much time do we have? 18 minutes. Okay, so we all know I do 20 plus minute videos, so you all got to suffer through some more rambling. So I've covered the drive. I've covered the power for the drivers. I've covered the 12 volt situation, the SATA power connector situation, 3.3 volts. What haven't I covered? Covered the LDO. Well, I've basically covered all of the e-power stuff. So yeah, it's kind of simple. In theory, if you just do all of that, the VRM should fire right up, and that's it. And then you use your good old feedback mod for voltage control. Now, there is a few potential issues. There's a chance that the programming of the ASP1211, just out of the box, is dumb. So things like it has a ton of load line, like it has a massive load line on it. So if you try to push 200 amps out of it, it'll drop like a huge amount of voltage. There's not really a good way to deal with that. Which incidentally, oh boy, I just forgot about that. Well, nah, that's basically just more advanced feedback modding, so that doesn't really apply. Like, just IDing the circuit is the important part. What you do with it, like, I'll explain that when I actually, like, do the build of the damn thing. At least, yeah, I'll explain it when I do the actual build. It's not super important. Like, it's not core information for making an e-power. It's just fun things you can do to your feedback circuits to make them work better. Well, give them more functionality than if you just do a regular feedback mod. But yeah, some of the issues are basically the stock programming of the ASP1211 could be kind of awful. There could be a very low overcurrent protection. There could be a there can be a ton of load line on it. That's annoying. There can be a and by a ton of load line I mean that the load line looks something like this, where this side is current, so I, and this side is actually, you know what? Let's just use amps and volts. Basically, that there is a load line, and if you have a very steep load line, it means that as your current output increases, your voltage drops and drops and droops, and droops. So yeah, that's annoying. You'd want like a flat load line looks like that, and then your voltage is steady across the entire current output range. But yeah, this thing, a lot of GPUs come with very heavy load lines out of the box. So, for example, the RX 480 GTR, or one of the I have two RX 480 VR power boards, and I can't remember which one it is, but one of them, if you push 30 amps through it, it drops like 15 millivolts. Like, droops 15 millivolts intentionally. Like, it just does that. If you push 30 amps, it drops 15. It droops 15. So that's really annoying. And if this has a similar load line, then that could be kind of annoying. It should be possible to there's nothing stopping you from trying to wire up the I2C interface for this thing after you've turned it into an e-power. That's fine. This chip will have an I2C interface. Just there's no documentation on how the registers are set up. So, you're going to have a lot of registers with no information on what any of them actually bloody do, which is really fun. Though I guess it might be possible to like reverse, because I do believe there's an extreme overclocking BIOS for this card. And if that BIOS reprograms the ASP1211, it'll be actually really obvious from the BIOS which registers it hits. So it should be possible to, like, I could potentially fix that over I2C. So that can definitely be remedied, but if you're working on a card where you have no data sheet and there's no BIOS which eliminates load line, or, like, if you can't find a BIOS that takes care of the I2C issues that you want to take care of, you're kind of screwed. Because you don't have documentation for which registers do what, and these voltage controllers tend to have like 128 of them, and trying to go through them one by one and seeing what happens when you change the values is a terrible idea. So, yeah. Other potential issues are something like the voltage controller being stuck in low power saving mode, where basically the VR, like, instead of having all 8 phases running, you'd have like 1, which that would be seriously annoying, but the way I think that circuit works is that it actually has to be, the GPU has to put an input into that. So if that is not connected to a GPU, that should be non-functional and it shouldn't get in the way. Another potential issue is that the enable the enable pin will be pulled low. But again, that's one of those things that I think the GPU has to intentionally pull down. Not like so if you disconnect the GPU, it'll just sit high on its own. So that should also be fine, but it could potentially be an issue. And without the data sheet, that would be an absolute nightmare to troubleshoot. What else is there? That actually covers it, I think. So, yeah, that's kind of the plan. Oh, yeah, there's these issues. If we go to the back of the card, the power plane here kind of sucks. So it's very, nice thing, you have a ground plane right here. That's great. That's awesome. That's lovely. I think the ground plane is, the ground plane goes something like this. There's a pretty substantial ground plane. Though I might have to check that, because I'm not 100% certain that if this side of the capacitors is ground. It could be, because if you think about it, right, because this is ground on these capacitors, but there's nothing stopping them from having the leg of the capacitor just go all the way through the board to an internal ground plane. So then you could just have a V-core plane that goes all the way, to these caps, and then have a ground plane right here. And the reason why that would be super awkward is because, well, now you need to run wire, you need to build like a power bridge for your core, for your actual V-core. So that's annoying, but it is not a huge issue, but it's annoying. So yeah, that might be a obnoxious thing that I might have to deal with, but not a complete catastrophe. And ultimately, I don't really plan to use this on anything super high power consumption. Like, I wouldn't stick this on a GTX 480. I mean, it would probably be fine with that. It would actually, I'm pretty sure it would be an upgrade over the reference GTX 480 VRM, if I'm not mistaken. It's just like I have more powerful VRMs available than this that would work better in that application. Honestly, I think what I'd probably stick this VRM onto is something like my HD 5870, sort of older, lower end cards, things that don't pull a ton of power because just wiring this thing up is going to be awkward. And also, it's not like a proper power board. It's just a sort of generic Asus 8-phase V-Core VRM, GPU V-Core VRM. Which is solid. Like, it's a solid 8-phase. It's just not the most powerful thing ever. So if I'm going to be trying to e-power something like a GTX 480 or a 580 or 780 Ti, Titan series card, that kind of thing, I'd much rather have something with like 12 phases or 14 or 16, like not an 8. Just because those would actually like have those will perform better thermally. So what else is there? Well, that pretty much covers it. So yeah, it's a bit awkward on the power planes because you do need to bridge it to whatever you're going to be hooking it up to. But yeah, it's basically just a simple case of cut the card and then supply all the necessary voltages for everything on this side of the card to work. And you can figure out all the mounting points for those connections from where, things like this go. You can just use the resistance mode on the multimeter to check that. And other features I figured I'd point out on the card. This thing does have a dual BIOS switch. I mean, it's a high-end AMD card. The dual BIOS switch is kind of a staple feature of those. I think since the 6000 series, like 6970s have had BIOS switches, and then 7950s, 7970s have BIOS switches, 290s and 290Xs have BIOS switches, Furies have BIOS switches, 480s don't, Vegas have BIOS switches. Like, it's just a high-end AMD feature is to have a BIOS switch, which is kind of it's nice. That's a nice feature to have, in my opinion. It's too bad they destroyed BIOS modding on Vega, isn't it, though? So yeah. And this VRM right here is the VDDCI. That's the same high side MOSFET as what you have over here. And this low side MOSFET is a NXP PH. Did I get that right this time? Yes, I did. 2530AL. And that is a 2.4 milliohm MOSFET. So basically, what's going on here is Asus ran out of space for their two-phase VDDCI power, so they crammed the inductor and the capacitor in the worst possible position on the bloody card, like right where the LN2 pot goes. Like, great, lovely, awesome. So if you wanted to run this card on liquid nitrogen or even dry ice, right, you'd need to move this capacitor and that inductor to the back of the PCB. Oh, and even then, there might be some LN2 pots that won't clear these, which is just like, yay, awesome, why? Though these are pretty far away. Like, these should clear. Like, I'd hope these clear. This definitely doesn't clear a damn thing, though. So that's a major problem for running this card on LN2. But the other issue is, like, yeah, Asus ran out of space, so they went with a 2.4 milliohm RDS on MOSFET to basically get the same, get close to the same RDS on as two of these guys, because two of these in parallel is effectively 2 milliohms, whereas one of these is slightly more than 2 milliohms. So similar, per phase power capacity as over here, just more compact. And last note, so interesting thing about actually the capacitors, the high volt, like the plus 12 volt capacitors everywhere, which are rated for 16 volts because that's That's I think the most common like size for capacitors that will like, because basically the capacitor has to be rated above the voltage you're going to apply to it. So, and I think 16 is just the most common value for that. So all of the you know, capacitors on the plus 12 volts are, they're 16 volt Nichicons for rated for 5,000 hours. So FP series, so FP 5Ks. I mean, it literally says it on them. But these output capacitors are all 5,000 hours rated APAC capacitors. And interestingly enough, these are larger than these, which is kind of and the reason why that's interesting is typically the higher voltage capacitors are much, much larger than the low voltage ones. So I'm guessing what happened here is ASUS wanted, they wanted a certain size and like capacitance and endurance rating, and they couldn't get it from APAC because APAC's their general like cheap capacitor supplier for everything. Like on low end motherboards, even the 16 volt capacitors are going to be APAC. Like everything's going to be APAC, and on other GPUs, everything again is just like APAC capacitors everywhere. And then here it's like, oh yeah, for whatever reason, the 16 volt ones, they're from a different supplier, which is kind of interesting because normally you see all the capacitors on a card being exactly the same, like same brand, not same spec, because obviously the output ones are lower voltage. But yeah, I think that pretty much covers it, doesn't it? Cut the card, wire up a SATA power connector, do some feedback modding, you know, working power board. That's basically the plan. So yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave a comment or any questions down below. I hope this made sense. I'd actually really would like some feedback because on this type of video, because I have a really hard time like figuring out how to explain where I'm going with a project like this, because I know exactly where I'm going. I just went through this like a horrible freaking mess, though. At least I feel like it was a mess, and I'm honestly not sure where to like start it or how to lay it out. So yeah, I would like to hear your feedback on like how you found this. Like, does it make any sense? Should I not bother because it doesn't make any sense? Or like, yeah, basically that would be handy. Because the other thing is like I have thought about like maybe doing it in real life with like the multimeter and everything, but at the same time I feel like that would actually be potentially more difficult because I can't like scribble onto the thing I'm working on. So, and like switching back and forth between GIMP and the thing, you know, and real life and then back to just, that would be a disaster in my opinion. That would be really awkward. So, yeah, I'm not entirely sure if it's better if I do it like this and just talk about what you have to do in theory, because again, it might turn out that when you start measuring things, it might turn out that things aren't wired the way you expect them to be, and then you're kind of screwed. But yeah, I'm basically just interested. Does this make sense? Because yeah, like the point is hopefully that you can kind of get an idea of how to build your own e-power out of, you know, a card that, you know, because if you get into extreme overclocking, you're going to start going through hardware, because eventually you're just going to go like, yeah, we need way more V-core, and then the thing's going to die, and then you'll have something that, you know, you might have a perfectly functional VRM, but the rest of it's dead. So, you know, this is kind of useful because then you might pick up something that is functional but has a garbage VRM. So you can steal the good VRM off of the good dead card and put it on the living card with the terrible VRM. That's kind of the whole point of the E-Power anyway. So, yeah. Either way, interested in your feedback. And let's end it here. If you'd like to support actually hardcore overclocking, then I have a PayPal, Patreon, t-shirts. You can find a link to all of that down in the description below. And that's it for the video. So thanks for watching and goodbye. Now where's that stop button? There it is.